For exam problem 1, we are solving for the overall mass flux of the system corresponding to the maximum molar diffusive flux. Now, the big principle to note here is because we're in a closed system capillary, that means that the maximum molar diffusive flux has to be equal to 0 because there's no change in the system, meaning that the maximum flux for water is equal to the maximum flux of deuterium, and the fact that they have to be equal to 0, so they're equal and opposite. Now, based off of that, what we can actually do is, using the molecular weight of each substance, we can multiply that by the maximum molar diffusive flux. For water, that's 2.78. For deuterium, that is negative 2.78. And if we actually multiply those together, we can actually convert the units into the mass flux for both water and deuterium. And from there, we can actually take the sum of that to get the overall mass flux, which is equal to negative 5.2, because that maximum flux is going to occur right in the middle at the 5 centimeter mark. So that's how we get the answer of negative 5.2 for the overall mass flux for question number 1. For question 2, we're making an order of magnitude estimate for the maximum driving force for diffusion. We're starting using equation 1-27, which contains the molar diffusive flux, the components, as well as the molar concentration and the Maxwell-Stefan coefficient. So first we're going to break it up into each of its two components, and again, drawing on the fact that we're in a perfect mixture and in an enclosed system, we can say that the molar fluxes add up to 0, and from there we can say that J1 is equal to negative J2 if we just subtract that over, meaning that we can actually get rid of this J2 term right here. And because the components have to add up to be equal to 1, we can again rearrange the equation to substitute out this y2. When this equation goes away, we're left with the negative J1y1 minus J1 plus J1y1. We can get rid of these two terms right here and they cancel out, which leaves us with this equation right here to solve for our estimate guess using the given information of 2.78 for this, as well as this number. We first solve for the molar concentration of the system by first solving for the mass concentration of each component in the middle, which we can do for because it's an ideal mixture. And then from there we divide by the molar mass for both water and deuterium, and then those give us a concentration of roughly 50,000 moles per meter cubed. From there we can plug these terms into this equation and we end up with roughly 55,000, or 10 to the 4th for our order estimate for problem 2 and our answer. Thanks.
For problem 3, I'll be pointing out just a couple of the important things to note in the graphs. In the top row, you can see here we start out with water's density before we move. As we reach that 5 centimeter mark, it switches over to deuteriums. As we reach the 60-second and get out of that 0.1, you'll notice that it's a more gradual drop instead of a sharp one as seen before. Before in the final, as the time is infinity, we notice that deuterium's higher due to its larger density. When we get to here, we notice again a pretty steep drop, although deuterium comes out lower, once more exhibiting kind of a less steep drop as we get out of that 0.1 second mark. But this time we have water being larger than deuterium. When we get to the mass flux, you'll notice when they reach that gradient that they both go up to their, not mass flux, but the molar diffusion flux. For the molar diffusion flux, when it reaches this 5 centimeter mark, it goes up to the maximum molar diffusive flux for water, and because we're in that closed system, it's the reciprocal, the negative 0.27 or 0.278 for deuterium. As we get to 60 seconds, you can see it's not as large of a spike for both of them before, as we reach infinity, there is no molar diffusive flux. Last, when we get down to the mass flux, you'll notice a strong spike at that 0.1 second mark, a smaller, more gradual spike right here at the 60-second mark. For the mass flux, as we hit infinity, it just levels off and there is no mass flux. That is problem 3. Thank you very much.